Now we're going to look at a free response question that has exponential functions in it. So this was on the AB exam. So let's look at what they're giving us. They're giving us the graph of f prime, and they're telling us that this graph is defined by another function g of x. So g of x is this graph from -4 to 0. They're not giving us the equation, but they are giving us the equation of this portion of the graph from 0 to 4. Okay. And it tells us that the graph of this f prime is continuous, which we can see. And then this point right here is -2. And this point right here is 3 natural log of 5/3. Those are your x-intercept. And this is a semicircle. And then they actually give us a point on f, which is not shown, but they do tell us that f of 0 is exactly 5. Okay, so let's go through and see what they're asking. So from -4 to 4, which is this graph that we're shown, find all values of x. So I want my x values only, at which the graph has a point of inflection. So as soon as you see those words, you should be thinking, I need my second derivative somehow. But I'm only given the graph of f prime. But what you should be thinking is the connection is that I know that the second derivative of f is really the same as the slope of f prime. So that's what you should be thinking. And in order to find points of inflection, I need where the second derivative is 0 or does not exist. And so really what I'm looking for on the picture is where is the slope of this graph is 0, or the slope of this graph does not exist, because that's going to be f double prime. So I notice that the slope of this graph 0 is at -2. And notice here, the slope of this graph is not going to exist at x equals 0 right here, because we've got that cusp. So those are those two values that I'm looking at. Now, in order to have a point of inflection, what else has to happen? The sign of the second derivative has to change, but the sign of the second derivative is the slope of this graph. So where is the slope of this graph changing? So let's check. At -2, the slope of this graph is going from negative to positive. So that's a point of inflection. Here, the slope of this graph is going from positive to negative. So both of these are points of inflection. So you can define this once, and you can say because f double prime changes signs. And you don't have to tell it what it changes from. Now, if you don't make this connection here and just put that here, then you would not get the full credit. You have to somehow make the connection to here. Or the other way you can justify it is you can justify it with f prime, but then you could say f prime changes from increasing to decreasing or decreasing to increasing. And that would be fine. So either this, showing this connection, or this statement by itself. Okay, part B. They want you to find f of -4 and f of 4. You're given f prime, the graph, and part of that equation. So in order to find f of -4 and f of 4, you should at least be thinking, okay, I need to take the antiderivative of f prime. So I'm thinking this. So let's start with the -4 piece. I want to figure out what happens to -4, so -4 should be one of the bounds that I use. Now, the only other bound that they give you information about is 0. So that's how I know that I want to use f of 0 is equal to 5. So this is the bound you have information about. This is the bound you're trying to find. So these are my two bounds that I'm going to use. So I'm going to use -4 and 0. And this is my fundamental theorem. The antiderivative of f prime is going to be f. We plug in the upper bound, which is 0, and we subtract off the lower bound. This is the setup right here. So this was given. This we know is 5. This is what I'm trying to figure out. This we're also going to find. This is the area underneath the graph of f prime from -4 to 0. So if I look back to this graph, here's my graph. Really, that's the area underneath this little semicircle from -4 to 0. So I'm looking for this area right here. So notice that this is a rectangle right here. So the area of that rectangle is 8. And then if I subtract off the area of this semicircle, that'll give me this leftover shaded region, which I'm looking for. The area of that semicircle is pi r squared divided by 2. So this is going to be 2 pi. So that is this piece right here, which is 8 minus 2 pi. Once I have this set up, I can solve for f of negative 4. So f of negative 4 is really 5 minus all of this. And again, you can leave it like this. It does not need to be simplified. Okay, now there's another part to part B. It's also asking for f of 4. You're going to do the exact same thing. You should be thinking, I'm going to take the antiderivative f prime. I want to use 4 as one of my bounds, and this is the bound that's given, so I'm going to use the 0 again as well. So I'm going to go from 0 to 4. Antiderivative f prime is f. Plug in the upper bound, subtract off the lower bound. Okay? In this case, this is what I'm looking for. This is 5. This is the area underneath the curve from 0 to 4. It would be this and this. But this one, they actually gave me the equation, so I'm not going to do it geometrically. You're not going to be able to actually find it geometrically, but I can go ahead and take this antiderivative. So this is my equation. They're giving me this equation. Okay, so let's take this antiderivative. So again, I'm just going to do each piece separately. So the u in this problem is negative x over 3. Your du is negative 1/3. So remember that whole reciprocal idea? So this would be a negative 15 e to the u. The antiderivative of 3 is 3x. I have bounds 0 to 4. Okay, let's plug it in. Negative 15 e to the negative 4/3 minus 12. Minus, if I plug in 0, be careful, if you plug in 0, this is e to the 0, which is really 1. So I have a negative 15 still there. If I plug in 0 here, this becomes 0. So this becomes plus, so this becomes plus 15, so plus 3. So all of this is this piece right here. This is equal to f of 4 minus f of 5. So all I need to do is move that 5 over. And this is what f of 4 is. Okay, last piece, part C. It's asking me to find the x values only for absolute max. So again, we start with critical numbers. Absolute maxes can only occur at critical numbers, which is where f prime of 0 does not exist. This is the graph of f prime of 0, so I see a 0 at 2. And then they also told me there was a 0 here, which is 3 ln of 5/3, which they told me what that value was. Now, typically for absolute maxes, we also check endpoints. Okay, so x equals negative 4 is a possibility. X equals 4 is a possibility. Now, let's check all our possibilities here. Now, I can rule out x equals 2 right away because in order for me to have a max, there has to be a sign change in f prime. There's no sign change on 2. So that can't be a max to begin with. Here, the sign change is going from positive to negative, so that is a max. It's a local max, but it could be absolute as well. And then these are my endpoints. Now, typically what we do is we take all of these, plug it back into the original function, which you can do, but then you would have to go back to what we did in part B. But we actually don't need to do that here. Notice here, the sign of the derivative always goes from positive to negative here. So that means the function from negative 4 is always increasing until it hits this value. So increasing, and then when it hits this value, the function starts decreasing. So this local max has to be your absolute in this case because the sign change, there's only one sign change going on. So you can justify it using the sign chart. So because f prime changes from positive to negative.